Our next topic will be parallel plate capacitor. That is very important and more oftenly asked in the board exams or even home exams. So this is going to be very crucial for us. So let's get started with the parallel plate capacitor. So imagine we have two plates of this sort, two parallel plates, very thin plates made of any whatever material, that does not matter, and this plate is given positive charge and this plate acquires the same negative charge, okay, and that is, this is plus Q and that is minus Q, and that conductor is earth to the ground, or if you don't draw this, it does not matter. So for the sake of now, just remove this, okay. We don't want to draw this, if it does not make any sort of complicated sense. This is being only drawn to show that the other side of the conductor is earth or grounded. Now what is the structure? This surface area of the plates are A each, and the separation between the plates is a small d. Okay, these are the physical structure of surface area A at separated distance of d. So we shall be having three steps. First step is to calculate electric field between the two plates. Number 2, we shall find the potential difference between the plates. And number 3, we go for C is equal to what? Charge upon potential. Very importantly, remember these three steps will be done in all sort of capacitors. Mainly we have three steps. First you find electric field. Maybe the shape is not of this sort, it may be spherical, it may be cylindrical, whatever. In all those categories we do what? First calculate electric field and then the corresponding potential, and then we find then we go for what? C. Okay, so first let's calculate the electric field between the two parallel plate capacitors. Now if plus sigma is the charge density of the first plate, then obviously minus sigma will be the charge density of second. So in the during the application of Gauss law, we learned about what? The electric field between one region, two region, or these three region. We did find electric field. So electric field between the field between plates E is given by what? Charge density over epsilon 0. Epsilon means the plates are placed in free space, that is the permittivity of the medium. And what is epsilon? That is charge over area, that is the value of sigma, and epsilon is here. So that is the electric field, and this electric field will be from negative plate to positive plate, remember, and this field will be uniform and its value is given by E or E vector E, whatever. The direction of the field will be plus to minus plate. Okay, now that is what we have done. So this first step is now done. What is the potential? So the potential between the plates, V is equal to, that will be done by the formula, that is dV upon dr is equal to E, only taking the numerical values. This dr gets multiplied by E. So potential is equal to what? E into R. We shall use this formula. So here potential between the two plates is the electric field between the plates multiplied by the separation between the plates. that is the potential between the two plates. So what is it? Q D epsilon naught into A. Very simple, do it very simply. And third step is C. So now the capacitance of the arrangement, the C for the system, C for the system so the capacitance of the system is according to this formula. You must be getting the how much charge we have given. The bar is Q. The plus Q minus Q does not matter. Only take the magnitude, that is Q. So C is equal to, okay, C is equal to charge over potential or voltage. How much charge has been given? Q. What is the potential? Q D over epsilon naught A. So this is cancelled and we get epsilon naught A over D. So C for the capacitor of this arrangement is epsilon naught A over D. Now see the formula. Epsilon naught is something you call constant, or it depends on the nature of material or nature of space between the two plates. For this sake, this is air, so we are considering there is epsilon naught. And what else? If the size of the plates are larger, the system has more capacity. If the separation between the two plates is small, then even the capacity is increasing. So the capacitance of a parallel plate capacitor depending on its physical structure and configuration. That's why it is always said the capacitor does not depend on the nature of the plate, that is material, what is made of. It rather it depends on the in between the medium and what physical structure. Okay. So this is epsilon naught A over D. It gives us the idea that this C So remember, we must follow the 3-step rule. That is, first you find electric field and then potential and then finally the capacitance. The C is directly proportional to A. More is the plate area, larger is the capacitance. C is directly proportional to 1 upon A. That is, less is the separation between the plates. T is less, then capacitance becomes larger, or vice versa and so on. And C is directly proportional to what? Permittivity of the medium between the plates. Now if I remove air or vacuum and then place another medium, then what its formula becomes? Suppose I have placed this region has been filled with some other quantity, that is, this region has been filled out with some quantity of medium epsilon, that is permittivity of the medium between the plates. Then what will be the capacitance? This epsilon gets shifted. Then C is equal to epsilon A over D. Remember, we are not changing any sort of value, A and D. Okay, this is the new formula for the capacitance. When the medium between the two plates is not air or vacuum, it is some other material like paper or any plastic, or you can put any metallic object, whatever, any sort of oil. Commercially, the oils are placed between the two plates, or any sort of papers. Okay. Now coming back to the first chapter that we studied about the dielectric constant, we had a term, that is epsilon is equal to dielectric constant and epsilon 0, and that was more precisely written as, this was equal to epsilon naught R and epsilon 0. We shall not using epsilon R, that is relative permittivity of the medium. we are using here what? K, the dielectric constant. So this is say my equation first, and that is equation number 2. Then from equation 2, C is equal to K epsilon 0 A over D. Now if I name this term as C naught for when the medium was air, that is denoted by this. So I get, this is my C naught. So C, that is K and C naught. Okay, very simple. This is the capacitance of the system when the medium was air, and it gets multiplied by the dielectric constant of the medium placed between the two plates now, and its final value becomes this. So, and we never have K equals to negative. It may be 0 or it may be infinity. It varies from 0 to infinity. It cannot be negative. But nowadays we have been discovering about the materials with negative dielectric constant. Okay, that's not a part of lecture today. So the C is always greater than C0. For example, if I put water, then for water, K is equal to how much? Remember, it is 80. Then it gets multiplied by 80, that is the capacitance of the system becomes 80 times greater than that with air. Okay, so this is the today's discussion regarding the capacitance of parallel plate capacitor. Tomorrow we shall be discussing about what the capacitors with, we shall place some dielectric medium or some plastic medium or any conducting medium. So we have to do lot more, little more calculation, not more than. Before that we shall be discussing with some nature of the dielectric properties. Okay. Okay, so note down all the things. If any doubt, we shall be discussing in the next video. Till then, bye and take care and have a wonderful time with you.